Okay, welcome. This is Vectors Part 3. Now we're going to learn how to add vectors analytically. At this point, you should know how to draw a vector to scale and then add vectors graphically by drawing them to scale. So by adding them analytically, we are going to calculate the resultant vector. And remember, the resultant vector goes from where you start to where you end. So the first thing I suggest is to draw a sketch of the graph, a sketch of the vectors. You don't have to draw exact relative scale. You know, this one appears that B is a little bit larger than A, and A is going off to the east or the right, and B is going up or to the north, or whatever the story goes. And then the resultant goes from the beginning of A to the end of B, and the angle of R is, of course, between the R and A. So whenever we add them, whenever we draw them out and they come out to be perpendicular, then we can easily use the Pythagorean theorem in order to find the magnitude. Recall that r squared, the hypotenuse squared, is equal to the sum of the square of the legs. So that's a very familiar calculation that you learned in mathematics, and so that should be fairly easy to do. But remember, it only works for right triangles. Later on, we may do some non-right triangle analytical calculations, but for now, we're just going to deal with right triangles. Then we use trigonometry to find the angle. So we find the magnitude using Pythagorean theorem. We find the angle using trigonometry. So we'll review that before going on. The trigonometric functions, as you recall from math class, is used to calculate the angles, but we're actually going to use the inverse of the trigonometric functions. As you may recall, the sine of the angle is defined as the ratio of the length of the opposite side to the length of the hypotenuse, the cosine, the length of the adjacent side over the length of the hypotenuse, and the tangent is the length of the opposite side over the length of the adjacent side. One more warning, this only works for right triangles. So we're going to use one of those to calculate our angles. We're going to use the inverse of them. So to find the angle, we are going to, if we had a drawing such as this, this angle represents, the inside that triangle. So we use the inverse of the tangent to find theta, and it's equal to the length of B, or the ratio of the length of B to the length of A, and we use the inverse tangent function. We'll do an example, and I'll show you what keys to press on your calculator in case you've forgotten. So for example, here's a very simple, I just put numbers in. The blue one is 35 units, and the red one is 15 units. They do form a right triangle. So to calculate the resultant, we use Pythagorean theorem. So we take the square root of 35 squared plus 15 squared. I suggest you do all this in your calculator at once by using parentheses. So you're going to start out with the square root function, and then in the parentheses around the 35, so you'll end up putting parentheses at the beginning and the end. Your calculator may automatically do that. Then you do 35 squared plus 15 squared, and then hit equals, and you should end up with 38. You should try that yourself right now, so to see if that in fact is what you get. Of course, I rounded that using significant digits. To get the angle, so now I'm going to find this angle since it's inside the triangle. It's going to be the ratio. We use ratio 15 over 35 and the inverse tangent function. If you do that in your calculator, I suggest you do that all at once also. So you to calculate that, you should end up with 23 degrees, and here's a hint on how to do that. So you do the second function, tangent, and that may produce this on your calculator screen, and then parentheses 15 divide 35 close parentheses and then equals. If you do it right now and you end up with 0.40489, you're in radians. So you have to make sure you change your calculator to degrees mode. If you're not sure how to do that, you can ask. You can also Google it for your particular calculator. But be sure you're in degrees, because we're not going to be using radians for these angles. Okay, so that's the basic idea. We use Pythagorean theorem to calculate the magnitude, and then the inverse function trig function in order to get the degrees. I don't know where the meters came from the 38. I must have left them off the 35 and the 15. Forgive me for that. Okay, so here's an example. We're going to analytically add, which reminder, we're going to find the magnitude and the direction of these two vectors. We have 150 meters per second due east and 65 meters per second due south. So as you can tell, east and south are 90 degrees from each other. So I'm going to do a quick sketch of that. So I first draw my 150 meters per second pointing to the east. And then because I'm adding vectors, I'm going to put the 65 meters per second due south on the end of that. And so I have that. My resultant is going to go from this open tail of the blue one to the orange one. So there's my resultant, labeled R. So I'm going to first calculate the magnitude of R. So to do that, I'm going to put this in here. I'll pause for a second while you catch up. Or you can press the pause key if you need a little bit more time. Okay, so once you have that, you should end up with about 163.6 meters per second, because we're both in meters per second. To get the angle or the direction of R, it's very conveniently an angle theta that I'm putting in here, that it's just going to be south of the east line. So now I'm going to set up my ratio. So I have the opposite side, I have the adjacent side. So again, I'm going to use the inverse tangent, and then I'm going to put 65 over 150 in my inverse tangent function. I'm going to calculate that. Go ahead and do that, or pause the video while you do that. Then you should get 23.4 degrees for that. So that means that angle's there. Then I clearly state the answer as 164 meters per second at 23.4 degrees south of the east. So be sure you state your answer with the magnitude and the direction. Don't just leave them in the calculations, because if they're not near the drawings, I may not be able to find them. Okay, so that's our first example. Here's a second example. We have 275 kilometers per hour, 20 degrees west of south, plus 150 kilometers per hour, 70 degrees west of north. So I conveniently designed this. So we're going to get a right triangle out of this. That's labeled 20 degrees. So I'm going to draw from my south line. I'm going to go 20 degrees to the west. So again, you're just sketching this. You don't have to measure anything out. It's approximate, just to kind of give an idea of what the result is going to look like. Label this 275 in my drawing. I'm then going to put on the end of that. So I need a north line. I'm going to measure 70 degrees west of that north line. So it's going to go that way. And that's where my angle's at. And coincidentally, that comes out to be a 90-degree angle. If you recall from geometry, we've got the Dash lines are parallel. If that's 20 degrees, then the alternate interior is 20, and 20 and 70 makes 90. So the problems that you're going to be getting will be making a 90-degree angle. I won't throw something in there that will surprise you. Label that 55 degrees, and the resultant is, of course, from the open tail to the open head. That's a resultant. So to calculate this Pythagorean theorem, I'm going to use the 55 and the 275 in my calculation. You can pause the video while you calculate that. Now you should have got about 280, and this is in kilometers per hour because both of those are. To do the angle, I built this so that it's a little bit tricky because we can find angles inside of the triangle. So I first label the angle that I'm going to be finding, and I chose to do that one because with that angle I have the opposite side and the adjacent side again. So once again I'm going to use the tangent function. Almost always, most of the time we use the tangent function, but just be careful that you can see inside the triangle that that's the angle that you have. So I take the opposite as 55 over the adjacent 275, and I calculate that. So I get about 11.3 degrees, and the 11.3 degrees is inside that triangle. So I don't have a reference. It's 11.3 degrees west of the 20-degree angle, so that doesn't make any sense. So I simply take the 20 and the 11.3, add those together, and now I can state my answer as 31.3 degrees, and now I'm going west of south. And so if you only look at the resultant, then you'll see that, the angle goes from the south all towards the west, and that's 31.3 degrees. Pretty straightforward. So remember that you should make a sketch so you can see what is happening. Show your calculations for your magnitude. This is a minimum amount of showing. You don't have to show the square numbers. Just show what you're putting in your calculator. Show the angle that you're calculating and label where that's located. And then if you need to do this sort of thing, you can put a justification on how you went from 11.3 to 31.3. And then, of course, state your answer with the magnitude, units, and the angle with, of course, the reference in it. Okay, so for your homework, you're going to do practice 3 in your notebook, and that's on the practice sheet that I gave you at the beginning of the week. Okay, any questions, get a hold of me. Bring your work to school, and I'll take a look at it. All right, thanks for listening.